Welcome to part 2 of chapter 7 on asymptotics. In this part, we focus on recurrence equations and their solution. What is a recurrence equation? A recurrence equation is a recursive definition of a function, and then we are interested in analyzing the rate of the growth of a function that is defined recursively. We will consider three recurrences. Let's start with the first one. In the first recurrence, f of n is defined recursively as follows. The base case is when n equals 1, f of n is defined to be 1, and the reduction rule, when n is greater than 1, is f of n equals n plus f of n divided by 2. Now, notice that n might not be even, and therefore we round down the quotient or the result of dividing n by 2. Now, you may ask two questions. One question is, why is this recurrence interesting? And the second question is, what is the rate of growth of the function f of n, which is defined recursively? Let's start with the first question. Let's give you some motivation why a function that is defined by such a recurrence is of interest. I will define a similar function. I will call it f hat. F hat is 0 in the base case, and it uses the same reduction rule. So the only difference between f hat and f is in the base case. I'll leave it as an exercise to prove that the relation between f and f hat is that f equals 1 plus 2 times f hat, and that in fact implies that f has the same rate of growth as f hat. So let's talk a little bit about f hat first. Consider the following algorithm that is computes the maximum of n numbers, and let's assume that n is a power of 2. Okay, the base case, how do we compute the maximum of n numbers? Well, the base case, if n is 1, if we're given a single number, then the maximum is simply the first number or the only number. The reduction rule, if you have more than one number, and again, we're talking about an even number of numbers, in fact, the power of 2, then what you do is you take pairs of your numbers. Let's say you take x1 and x2, you take x3 and x4, and so on, and you compare them, and you let yi denote the maximum of x2i minus 1 and x2i. So y1 is the maximum of x1 and x2, y2 is the maximum of x3 and x4, and so on. So as a result of this reduction stage, we are left with n over 2 yi's. Now what we do is we apply the procedure recursively, and we apply the maximum to the y1 up to yn over 2. So I think you all see immediately that this procedure is correct. It in fact computes the maximum of n numbers. It's a kind of a non-standard way of computing the maximum of n numbers. It's of interest, of separate interest, not because it reduces the number of comparisons that you need to perform in order to compute the maximum of n numbers, but because one can parallelize this procedure and in fact build a circuit that computes the maximum of n numbers based on it. But let's leave this aside. At this point, we haven't defined what circuits are, etc. So let's focus on the number of comparisons that this procedure requires. And the claim is that the number of comparisons that are needed to execute the maximum of n numbers using this procedure equals f hat of n. And let's try to understand why. Well, if n equals 1, then you don't do any comparison, and therefore the number of comparisons is 0. And if n is greater than 1, well, you do n over 2 comparisons. This is what you see over here. This is the term that you see over here. And then you apply the procedure recursively with n over 2 elements. And therefore, if this number equals the number of comparisons that you do in the recursive call, then this number equals the total number of comparisons. And that proves the claim. Okay, so I think that we answered the first question, namely, why is f of n interesting? Now, let's address the second question. Let's try to analyze f of n. And the following lemma states that the rate of growth of the function f is big theta of n. So f has in fact a linear growth. Now, how will we prove this lemma? The proof goes in two stages. In the first stage, we will prove it for the case in which n is a power of 2. And the reason that we will focus on powers of 2 is very simple. It's because of this floor function. It's a very annoying function, and we want to ignore it. And in fact, we can, because if n is a power of 2, then n is even, and then the floor of n divided by 2 is n divided by 2. And when you recurse, you will do n divided by 4, n divided by 8, and so on. And because n is a power of 2, the floor function will never be important. So that's the reason we focus on powers of 2 in the first part of the proof. In the second part of the proof, we address the case that n is not a power of 2. And then, of course, we're left with a question: what happens if instead of a floor function here, we would have a ceiling function? Okay? So let's start with the first part of the proof, namely analyzing the rate of growth of f when n is a power of 2. Okay, so we claim that f of 2 to the k is 2 times 2 to the k minus 1. Now, you may ask, how did I come up with this expression? Okay, we will talk about that. But first, let's prove that this equality indeed holds. And the proof is by induction on k. The basis for k equals 0. We plug in f of 2 to the 0 is f of 1. F of 1 is 1. 2 times 2 to the 0 minus 1 is 1, and we get equality, and that completes the induction basis. The induction hypothesis is that the claim indeed holds for k, and now we are dealing with the induction step. F of 2 to the power of k plus 1, we apply the reduction rule, is 2 to the power of k plus 1 plus f of 1/2 of the argument, namely f of 2 to the k. Now we apply the induction hypothesis, we replace f of 2 to the k with 2 times 2 to the k minus 1, and we arrange the terms, and we get what we need, and that completes the proof. Now, this proof is very easy if you have a good guess of the solution. But how do you come up with the guess of 2 times 2 to the k minus 1? Okay, so if somebody asks you, is this guess correct, you can check it by induction, but how do you come up with the guess in the first place? Okay. So let's consider a second version of the proof. We want to prove that f of 2 to the k equals 2 times 2 to the k minus 1, but in fact we don't have this guess, and we're trying to figure out this guess. And this slide shows you the end of the analysis. Let me show you the analysis stage by stage. So we want to analyze what f of 2 to the k is. Right? This is our goal. Now we know that f of 2 to the k is 2 to the k plus f of 2 to the k minus 1. So let us call this part, this term, let's call it the penalty. And this part is the recursive value. Okay? So we can decompose f of 2 to the k to two parts, the penalty and the recursive value. So let's write the penalty. So the penalty here is, the penalty here is 2 to the k, and the recursive call is f of 2 to the k minus 1. Right? So we know, in fact, that f of 2 to the k is the sum of the penalty plus the value of the recursive call. Now, the recursive call we apply again the recurrence, and we get a penalty of 2 to the k minus 1. And now we get a recursive value of f of 2 to the power of k minus 2. And again, we get a penalty, 2 to the k minus 2. And we continue in this fashion until we reach the base case. What is the base case? The base case is f of 2 to the power of 0. This is when the recursion ends. When the recursion ends, we know that the penalty, there's only a penalty. The penalty is 1, because f of 2 to the 0 is simply 1. Okay? What do we conclude? So we have here all these penalties, and we conclude that f of 2 to the k is simply the sum of all the penalties. Right? The sum of all the penalties is 2 to the, let's write it like this, is 2 to the k, this is this penalty, plus 2 to the k minus 1, this is this penalty. I did not draw the arrow over here. Plus 2 to the k minus 2, plus, until we reach 2 to the power of 0. So we're summing up all these penalties in order to determine what f of 2 to the k is. But what is this summation? This is a geometric sequence. We know what this value is. It is 2 times 2 to the k minus 1. Okay, so this is how you derive your guess, which you could prove if you want by induction, if you don't trust this analysis. So the point I want to emphasize in this proof is what I actually did is I built a recursion tree. This is a recursion tree where I follow the recursive calls, and next to each recursive call, I write the penalty. So the penalty associated with the first recursive call is 2 to the k. The penalty associated with the second recursive call is 2 to the k minus 1. And the penalty associated with the last call is 1. And all I have to do now is sum up all these penalties, and I get that the sum of all the penalties is what I wanted to prove. This is a very important technique in which one tries to analyze the recurrence equation by unrolling the recursion. Another way of writing it would be to write f of 2 to the k is 2 to the k plus f of 2 to the k minus 1, copy the 2 to the k, expand f of 2 to the k minus 1, and continue in this fashion, and you get this thing. This is exactly the same type of analysis that is applied here, but here it's applied in an algebraic fashion, and here it's applied using a tree, a directed rooted tree. Okay, so now I need to address the second question, right? So we have shown that for powers of 2, f of n is 2n minus 1, which is big theta of n. But what happens when n is not a power of 2? For this, we apply the following lemma. So assume that I have two functions, f and g, both of which are monotonically non-decreasing. And assume that the function g is well behaved in the following sense. When I multiply the argument of g by 2, the value of the function increases by a factor of at most rho, where rho is some constant. Now, if I have these two conditions, monotonicity, and g is well behaved, namely when I multiply the argument by 2, the value of g does not increase by too much, then if f is big O of g with respect to powers of 2, then f is big O of g with respect to every n. If f is big omega of g with respect to powers of 2, then f is big omega of g with respect to every n. I will prove the first part, and I'll leave the second part as an exercise. Make sure that you know how to complete the second part of the proof. Okay, so the claim is that if f and g are monotonically non-decreasing, if g is well behaved, when you multiply the argument by 2, g increases by a factor of its most rho, and f is big O of g with respect to powers of 2, then we want to prove that f is big O of g with respect to every n. Okay, now, f is big O of g with respect to powers of 2 means that there exists a constant, and there exists a uppercase k, such that for every lowercase k, which is greater than the uppercase k, f of 2 to the k is less than or equal to the constant times g of 2 to the power of k. This is exactly this statement. Okay. Now you give me an n, which is sufficiently large. How large should it be? It should be greater than 2 to the power of my uppercase k. This is this k. Now, I take my n, and I can sandwich it between two powers of 2. It is greater than or equal to some power of 2, 2 to the power of lowercase k, and strictly less than 2 times 2 to the power of this lowercase k. Okay? So, of course, this lowercase k is going to be greater or equal to this uppercase k. Good? Now, f of n is bounded by f of 2 to the power of k plus 1. Why is this true? Well, n is less than 2 times 2 to the k, and f is monotonically non-decreasing, so we get this inequality. Now, f of 2 to the power of k plus 1 is bounded by c times g of 2 to the power of k plus 1. This is because f is big O of g for powers of 2. Now, I know that g is well behaved. When I multiply the argument by 2, the value doesn't increase by more than a factor of rho. So I get this thing. So I just use this assumption over here. And now, I know that g of 2 to the power of k is bounded by g of n. This is because g is monotonically non-decreasing. So you see, f of n is bounded by some constant. The constant now is c times rho. This is my new constant. Times gn. So f is bounded by some constant times g, and this holds for every n which is sufficiently large, and therefore f is big O of g for every n as required. Good, so we have this lemma, and we have our recurrence, and we want to prove that f is big theta of n also when n is not a power of 2. We already showed this for the case that n is a power of 2. Now we're in the second part. Okay, so this is our recurrence. F of n is 1 if n equals 1. It's n plus f of n divided by 2, rounded down if n is greater than 1. And we know that f is monotonically increasing. I'll leave that as an exercise. That f of 2 to the k is less than or equal to 2 times 2 to the k. This we proved for powers of 2. Let's define g of n to be n. So we get that f of 2 to the k is big O of g of 2 to the k. G itself is monotonically non-decreasing and well behaved. When you multiply the argument by 2, g increases by a factor of 2. So by applying the lemma that we just proved, we get that f is big O of g. And we also, same proof also tells you that f of n is big omega of g. And that completes the proof. Now, the whole point that I want to emphasize is that I don't need to worry about the floor function. This floor function, which gives you a lot of trouble when you would try to get a clean expression for f of n. I don't need to worry about it. I just apply the lemma, and because f is big O of g for powers of 2, and g is well behaved, I can conclude that f is big O of g for every n. Let's look at the second recurrence. The second recurrence is very similar to the first recurrence. The only difference is the coefficient here, 2. Okay? That's the only difference with respect to the first recurrence. And again, you may ask two questions. Why is f interesting? And what is the rate of growth of f of n with respect to this new recurrence? So now the f is defined like this. It's not the old f. So let me start with some motivation. Again, I'll do a small modification. Instead of considering f, I'll define f hat. The base case is a little bit different. It's 0 instead of 1. And the reduction, instead of adding n, I add n minus 1. And the f and f hat are very similar. You can check this, that f equals f hat plus 2n minus 1. I'll leave that as an exercise. Now, let me motivate you what f hat is about. Consider the following sorting algorithm. This algorithm actually has a name in the literature. It is called merge sort. And this algorithm sorts n numbers as follows. Again, we assume that n is a power of 2. The base case, if n equals 1, you want to sort a single number, you just return the number. The reduction rule, well, you take the list of numbers, x1 to xn, and you split it into two lists, x1 up to xn divided by 2, and xn divided by 2 plus 1 up to xn. So these two lists are of equal length. Their length is n divided by 2. You sort each one of these lists recursively to obtain the sorted lists y1 up to yn divided by 2 and yn divided by 2 plus 1 up to yn. So the first list is the result of sorting the first half of the input. The second list is the result of sorting the second half of the input. Now, to complete the sorting of the input, you take these two sorted lists and you merge them. How does merging take place? Well, you scan each of the lists from the small number to the big number, and you compare the number you have, and you output the smaller number, and you advance the pointer of the smaller number, and you continue in this fashion. Now, the point that I want to emphasize is that the number of comparisons in this sorting algorithm equals f hat. Why is it true? Well, if n equals 1, we didn't do any comparison. We simply returned x1, so the number of comparisons is 0. And if n is greater than 1, and let's again assume that it's a power of 2, then I applied the recurrence. I applied the recursion twice to lists of half the size. So I have here two applications to lists of half the size. And then I had to apply the merging. And the merging requires n minus 1 comparisons, because once you're done with all but one element, you just put it at the end of the list. You don't have to do any comparison. That's why you have the minus 1 over here. Okay? So f hat measures the number of comparisons in this sorting algorithm, and therefore it's interesting. And f hat and f behave very similarly. So if we know how to analyze f asymptotically, we know how to analyze f hat asymptotically, and vice versa. Okay, so we answered the first question, and that is, why is this f interesting? Now let's try to analyze the rate of growth of f of n. We claim that the rate of growth of f of n is big theta of n log n. And again, the proof of the lemma will go in two steps. In the first step, we will deal with powers of 2, and then we will extend the proof to arbitrary values of n. Okay. So, for powers of 2, we claim that f of 2 to the power of k equals k plus 1 times 2 to the k. Now you may ask, how did I reach this guess? So, I will show you by using an argument which we used for the first recursion, the argument of analyzing the recursion tree. Okay, so I start with the evaluation of f of 2 to the k. My recurrence tells me that f of 2 to the k equals 2 to the k plus f of 2 to the k minus 1 plus f of 2 to the k minus 1. So I have these two recursive calls. So I have to take this cost plus this cost plus this cost, and the sum of these three equal f of 2 to the k. This is the recurrence. Now, each of these recursive calls incurs a penalty of 2 to the power of k minus 1 and creates two recursive calls with half the value. And we continue in this fashion. We obtain a binary tree, until we stop when we have an argument which is 2 to the power of 0. This is the stopping case of the recursion, the base case of the recurrence, in which f of 2 to the 0 is f of 1 simply equals 1. So now all we need to do is we need to add up all the penalties in this tree. Okay? So let's do the addition. We have the root. The penalty, we have one root, and the penalty associated with it is 2 to the power of k. Let's go to the children of the root. We have two children, that's the 2 over here. Each one of them incurs a penalty of 2 to the power of k minus 1. So when we do this product, we get 2 to the power of k. And we continue in this fashion. Each time the penalty is divided by 2, and the number of recursive calls is multiplied by 2. Right? So we're left with a total penalty, per level of the recursion, which equals 2 to the power of k. Finally, we reach the last level, the level of the leaves. The number of leaves is 2 to the power of k, and each leaf incurs a penalty of 1. So the total penalty is 2 to the power of k. So we see that within each level, the sum of the penalties is constant. It is 2 to the power of k. How many levels do we have? We start with k and we end with 0. So we have k plus 1 levels. So in total, we get that f of 2 to the power of k is k plus 1 times 2 to the k, as required. Now you may ask, what do we do when n is not a power of 2? Well, we know that f of 2 to the k is k plus 1 times 2 to the k. Let's define g of n to be n log n. Notice f of 2 to the power of k is big theta of g of 2 to the power of k because of this. Okay? Good. Now, both f and g are monotonically non-decreasing. Moreover, g is well behaved. When you multiply the argument of g by a factor of 2, the value of the function increases by at most 4, because g of 2 to the power of k plus 1 is 2 to the power of k plus 1 times the log of this, which is k plus 1. G of 2 to the k is 2 to the k times k. A log of 2 to the k is k. This ratio is 2, and this ratio, k plus 1 over k, is bounded by 2. So in totality, this ratio is bounded by 4. So g is well behaved. We can apply our lemma and conclude that f is big theta of n log n, as required. Good, so we solved the second recurrence as well. Let's look at the third recurrence. What is the difference between the first, second, and third recurrence? It is this coefficient. The coefficient over here now equals 3. Okay? It is not 1, it is not 2, it is 3. Now you may ask, what is the rate of growth of this function? Now, if you're interested in motivation in this function, we will show a circuit, the cost of which satisfies this recurrence later in the course. Okay? So let's skip the motivational part and do the analysis. And we claim that the rate of growth of this function is big theta of n to the power of log base 2 of 3. This is roughly, for those of you who are curious, this is roughly n to the power of 1.6. Okay? Now, how do you do this analysis? Well, you try to evaluate what f equals for powers of 2, and then you use the regular idea, the regular lemma that we used before. So let's try to do that again using the method of the recursion tree. When we try to compute f of 2 to the k, we get a penalty of 2 to the k, but now we have 3 invocations of the recursion with an argument which equals half the original argument. Each one of these recursive calls has a penalty of 2 to the power of k minus 1, and it invokes 3 recursive calls with half the value of the argument. So if the argument here is 2 to the power of k minus 1, the argument here is 2 to the power of k minus 2. And again, we continue. We write the penalties, and we continue to unroll the recursion tree until we reach the leaves. The leaves correspond to f of 2 to the power of 0, which equals 1. Okay? So now our goal is to compute the sum of penalties over this tree. Now this is not a binary tree, this is a ternary tree. The degree here is 3. You see, the degree here is 3 and so on. So in the root, I have 3 to the power of 0 nodes. In this level, let's call this the 0 level, let's call this level 1. In level 1, the number of nodes is 3 to the power of 1. In level 2, the number of nodes is 3 to the power of 2. And in the final level of the leaves, the number of leaves is 3 to the power of k. Now the penalty associated in each level is 2 to the power of k with respect to the root, 2 to the power of k minus 1 with respect to the first level, 2 to the power of k minus 2 with respect to level number 2, and so on and so forth, until we have reached the leaves in which the penalty is 2 to the power of 0. So now we want to compute the sum of these penalties. The sum of these penalties is written like this. It's the sum from I goes from 0 to k of 2 to the power of I times 3 to the power of k minus I. You notice that the exponents here have a constant sum. It is k. So it is 2 to the power of I times 3 to the power of k minus I. Let me take 3 to the k outside of the sigma, and I get 2 to the power of I times 3 to the power of minus I. This is what I wrote over here. And this is nothing but a geometric series. We can apply the formula for the geometric series. So the 3 to the k we copy, and we have here 1 minus the quotient. The quotient is 2 over 3. To the number of elements we're summing, it's k plus 1, divided by 1 minus the quotient. The quotient is 2 over 3. And this expression evaluates as 3 to the power of k plus 1 minus 2 to the power of k plus 1, and that completes the proof of the case in which the argument is a power of 2. Now, what do we do when n is not a power of 2? Let us define g of 2 to the k to be 3 to the power of k. Okay? Notice, g of n is 3 to the power of the log base 2 of n, because the k here in the exponent is the log base 2 of the argument. And by doing the standard algebraic manipulations, 3 to the power of log base 2 of n equals, this is equality, n to the power of log base 2 of 3, which is roughly 1.6. Okay. Now, what do we know? We know that f of 2 to the k is big theta of g of 2 to the k, because we know that f of 2 to the k is 3 to the power of k plus 1 minus 2 to the power of k plus 1, so it's bounded by 3 times g of 2 to the k, so it's big O of that, and you can also show big omega if you want. Now, both f and g are monotonically non-decreasing. I'll leave that as an exercise. G is well behaved. When you multiply the argument by 2, G increases by a factor of 3. And now you apply the lemma, and you conclude that F is big theta of G. And that's what we wanted to prove. Now, you may ask, what happens in the somewhat more general case where f of n is c in the base case and you have a penalty of an plus b plus f of n divided by 2 in this case. So this is like a more general case of the first recurrence. Okay, and of course we're interested in the cases where a, b, and c are constants. Okay, so we claim that regardless of these constants a, b, and c, the rate of growth of f is big theta of n. Okay, how do you prove it? Well, you follow the same method as before. You try to find out what f is for powers of 2, and then you conclude what happens from powers of 2 to arbitrary values of n. Okay, so let's try to analyze what f of n is. So we'll solve it for the case when n is a power of 2. So we have f of 2 to the k, we have the penalty, which is a times 2 to the k plus b, and then we have the recursive application, f of 2 to the power of k minus 1, and we have a penalty in this case, which is a times 2 to the power of k minus 1 plus b, and we continue in this fashion until we reach the base case, 2 to the power of 0, in which the penalty is c. Now we sum up all the penalties. We get the sum of all the penalties is summation I goes from 1 to k of a times 2 to the power of I plus b, because you see that the a and the b are constant here, and here we have exponents of 2 starting from 2 to the k, ending with 2 to the power of 1. And finally, in the base case, we have the c. We reorganize this expression, and we get a times 2 to the power of k plus 1 minus 2 plus bk plus c, and you can easily check that this is big theta of 2 to the power of k, as required. Second example, which corresponds to the second recurrence. Here again, we use the more general form, where the base case is c, and the reduction rule is an plus b, plus 2 times f of n divided by 2. All these a, b, and c are constants. Let's assume that they're positive constants, not 0, especially the c. It doesn't really matter, actually. It would matter if the a were 0. So let's assume that a is not 0. A does not equal 0. And the same thing over here, because if a here were 0, then it would be somewhat different. Positive. Non-negative, let's say. Okay, good. So, we're interested in this case, and we claim that the rate of growth of the function is, again, big theta of n log n, like in the second recurrence, even though we have here different constants. And how do you prove it? Well, you need to make a guess about f of 2 to the power of k, and you reach this guess by solving the recurrence, the recursion tree. So try to sum the penalties in the recursion tree to find f of 2 to the k, and check that this is indeed the number you get. Good. Let's see a third example. Consider the following recurrence, big F of k, in the base case where k equals 0, it's 1. If k is greater than 0, we have a penalty of 2 to the k. The argument is k, the penalty is 2 to the k, and then we apply f of k minus 1 twice. So this recurrence is somewhat strange because of two reasons. First of all, the additive term over here is exponential in the argument. And the second reason is that the recursive call is not to k divided by 2, but to k minus 1. Okay? So if we look at this recurrence, it seems to be totally unrelated to the previous recurrences that we saw. And I claim that big F of k is k plus 1 times 2 to the power of k, from which you can conclude that f of k is big theta of 2 to the power of k times k. Okay? Good. So how do we prove this lemma? Let's use substitution. Let's define lowercase f of 2 to the power of k to be uppercase f of k. Okay? So now, let's see what recurrence lowercase f satisfies for powers of 2. So f of 2 to the k, when k equals 0, is f of 0. F of 0 is 1. If k is greater than 0, f of 2 to the k is big F of k, which equals 2 to the power of k plus 2 times f of big F of k minus 1. So we have this 2 to the k plus 2 times big F of k minus 1. The big F of k minus 1 is the small f of 2 to the power of k minus 1. So we notice that lowercase f satisfies the second recurrence. So f corresponds to recurrence number 2. And because of that, we know that f of 2 to the power of k is big theta. Sorry, there's a mistake here. Big theta of k times 2 to the power of k. And therefore, f of k, which equals lowercase of f of 2 to the k, is k times 2 to the power of k. And that completes the proof. To complete this lecture, let's consider 2 more recurrences. The first recurrence is similar to the recurrence number 1, but here the penalty is not n, but a constant. So we have a constant penalty in this recurrence. You may ask, why is this recurrence interesting? Well, it actually asks how many times can you fold a rod of length n until it reaches a unit length. Okay? So if it has a unit length, then maybe you want to write here 0. It doesn't matter if it's a 1 or a 0. And if it is longer, you fold it, and now you're left with a rod of half the length. And you are actually counting, this function actually counts the number of times you fold the rod until you reach the unit length, or half a unit length in this case, because you also fold it when n equals 1. So it would be 1/2 of a unit length. Okay? Good. What is the solution to this recurrence? I'll leave it as an exercise. It's a very important exercise. It's important that you know how to solve this recurrence. Let's look at the second recurrence. In this recurrence, it's very similar to the recurrence number 2. In this recurrence, instead of applying f twice to n divided by 2 rounded down, or say to f divided by 2 rounded up, we apply it once with respect to rounding down and once with respect to rounding up. And you may ask, why is this recurrence interesting? And in fact, it's interesting because of this merge sort that we saw when n is odd. Because when n is odd, you divide the big list into 2 sublists, and they do not divide equally. So one will be n divided by 2 rounded down, and the other list will be n divided by 2 rounded up. And then you will sort each one of them recursively and apply merging. Okay? Now you may ask, what is the solution to this recurrence? Now the important thing I want you to notice that our method for solving the recurrences was not sensitive to whether I had here floor or ceiling functions. The reason was I solved these recurrences, first of all, for powers of 2. In powers of 2, the ceiling function and the floor function did not come into effect because I'm always dealing with powers of 2. So in powers of 2, all ceiling and floor functions can be ignored. Right? And we solved the recurrences for power of 2, and then from the powers of 2 we concluded what the solution is, the asymptotic growth is, for every n, using our nice lemma. This completes this lecture. Thank you.